See you too.
Well, I mean, Sim could figure out. I've actually got a pre-recorded talk, so she doesn't need to join until questions. So it might buy you a bit of time to figure that out. But we have great. Because it's pre-recorded, like the stream is going to be necessary for this because I'm not going to be speaking. So yeah, try and make sure things are working. If not, I can stream it through my webcam if it's causing significant problems. I'll just try sharing through Discord first. We'll see how that goes. Okay, can everyone see that? Someone's typing. Great. Okay, I'm going to hit play, and then three of us will answer some questions at the end.
Utilitarian decision-making in models, evaluation and steering.
In this paper, we evaluated Llama versus the Oxford Utilitarianism Scale, a 2018 psychology questionnaire designed to classify attitudes to utilitarianism versus deontology. We compared it against human responses to the same questions and measured the change in response as we tried steering and prompting. The OUS is a 2018 9-question psychology survey where each question is a statement rated agree or disagree out of 7. The questions are divided into 2 factors: instrumental harm, to what extent does the ends justify the means, and impartial beneficence, how do you value those outside close social circles? This gives us a 2-dimensional numerical quantification for moral behavior. We combined this with some human survey data, so we had a solid baseline for expected behavior. We set out to explore whether and how models may differ from human morality. Would steering help in understanding the real meaning of features? What kind of answers would we get if we asked Llama to answer by pretending it assumed the persona of a specific demographic, say it was a 27-year-old woman from France? Using Goodfire's API, we were able to run the questionnaire against a variety of different test conditions. We extracted the logits when parsing the response and computed the average response, so there was no need to sample the model multiple times or play with temperature, making this a very efficient framework for experiments. We analyzed the responses per question and summarized them to 2 factors using the averaging formulas of the OUS. We also ran some basic cleanup and analysis of the human dataset. Our first experiment was to evaluate the base model responses. After that, we tried steering the model with some hand-picked features. The labels for these features were often confusingly similar, so we hoped that we could understand them better by seeing their response. Separately, we tried prompting, considering the following statement as an American person, and so on. We used classes of people that matched the categories in our human dataset, so we could measure prediction error. Here we show the model behavior versus the human responses shown as a heat map. We found that both the 8 billion and the 70 billion models did not match the human responses well, or each other. The 8 billion model was much more prone to refusal, so we focused on 70 billion. For feature steering, we tested each feature by altering the strength of the steering from an ablation of -0.5 to an enhancement of +0.5. Different features moved around the 2 factors in different patterns, demonstrating a qualitative difference in their meaning to Llama. Most features tended to have some effect, typically with a strong steering leading Llama to higher levels of impartial beneficence, even if the feature label was irrelevant to morality. Then we tested the model's ability to impersonate demographics. Persona responses were found to be not aligned with human equivalent responses, nor with the responses from the base model. When comparing human versus persona model responses, Llama consistently mischaracterized human values, tending to overestimate impartial beneficence and underestimate instrumental harm. The graphs indicate the disparities between human and model answers for different nationality personas, grouped by continent. We found that the instrumental harm and impartial beneficence factors can be a meaningful and interpretable way to evaluate models. We also found that Llama is not a good predictor of human values, particularly for instrumental harm. Prompts did little to improve this. Finally, we found that steering can have unintended consequences for the model's decision-making. There are several limitations to our approach. Rating your level of agreement to a statement is not the same as an actual model dilemma. Models may give inconsistent or deceptive answers. We found that most of the variance only came from a few questions in the survey, which may indicate the results are not accurate. Also, without checking model internals, it's hard to include what is actually behind our paper's results and causing it. For future work, we'd like to see a better set of prompts and questions, perhaps adopting those of the greater good benchmark. We should also investigate why irrelevant features affect the responses so much, as this has important implications for using feature steering as an effective tool. Our work is indebted to the original Oxford Utilitarianism scale and the psychology researchers who validated it against so many peoples and countries. Our results also tie into the greater good benchmark. This paper was published last month that uses a similar questionnaire and factor model. They have a more robust question set and use it mostly for intermodal comparisons. Thank you very much, and thanks to Park Community and Goodfire for running the hackathon.
An excellent question. So it took us quite a bit of time, I think, to get the eval frame up and running. So it was, I think, only Saturday evening, like over halfway through the hackathon, before we really were able to start getting experiments going and starting to put together our conclusions. And that didn't leave us that much time between then and writing up. In particular, we had an awful lot of different hypotheses. The raw human data set we had was very rich. You can see we only really answered questions about the nationality. Those are the charts we actually show in the paper and in that presentation. But we were also looking at some of the other bits of data, notably gender and age. So we were trying to sort through things and find what was worth presenting and what wasn't. Again, there are also thousands of features for us to look at. So trying to find the interesting ones and trying to find good methods of sorting them. I discussed that a bit in the paper as well. Was also a challenge. Pandas, I think you probably looked closer into all the different demographic features. Did you have anything to answer on that one?
Yes, sure. Arcana, can you please, I had a connection drop for a second. Can you please restate the question, please? How did we, what do you mean by that?
So
If I can just
Yes.
Boris, I think it would help if you showed the image, if you can, or the slide with the demographics stuff.
this one? Well, we have some more charts
Yeah.
which not shown in either, but it'll take a bit of time to bring those up.
Yeah, I mean, this is the one I was thinking.
Yeah, so we did find like the responses are different for different questions, as you can see from this right-hand one. Not shown. We also analyzed age and gender a bit, and like if you make like some stereotypical assumptions, there were some like weak correlations there, by and large. But I think the nationality one was the most interesting, as there were a lot of sort of surprising cases there. And again, it kind of exposes the model's biases. So this one on the left here is showing what the model thinks an American is versus a Singaporean. What precisely why it thinks that cluster of countries are especially keen on instrumental harm, I don't know, but seems to be the case.
I mean, you mean a general kind of conclusion, if I have. Yeah, no, the previous one was quite different. Like there, we built an interactive web interface. Um, so here the interesting bit was the like that we could actually play with the features of the models, and then but also we could compare the responses with human responses. What was interesting also was that we could prompt the model to respond pretending it is, a 30-year-old, I don't know, person from a continent or a specific continent or country. And there were other categories. I mean, other ways we could categorize the personas from based on the human data, like education level, religion, and all that. But as Boris said, we had to kind of narrow it down, and given the time, we had to kind of like look at what is the most that we can get out of it. Um, Overall, I think like a good like they have been these hackathons have been great learning experiences for me in terms of collaboration, in terms of building my skills, learning, working with great people. And actually, one like thing in general I would say is to like just push through the whole like one kind of a key thing that I've concluded to is like you have to push through the whole weekend and submit, no matter what you think is no matter how good you think the outcome is, because you never know, like you know, you never know, and also like by actually submitting and like kind of completing the task, it feels fulfilling for oneself as well. So yeah,
I feel a fair amount of our success came from it was CNM's first suggestion for us to adopt this OUS scale. Before then, the project had some very vague ideas on like, oh yeah, maybe we're going to explore like moral choices by setting them trolley prompts
indeed,
or something. And I think that
indeed,
was really
indeed.
the break for like identifying, hey, this is actually a really interesting idea, and there's so much we could do with it, which is a bit why the project is spread in several places. But yeah, I think the initial suggestion there and having like the good idea is probably what makes or breaks a project. So thank you,
Indeed,
Sina.
in a very good point. Thank you, Zina. Thank you.
Hello, can you hear me? Yeah. Yeah, I can't share my screen for some reason. Um, no, the button is just cleared out for me, so I don't know if that's something I can do. Is this all right? Yeah, the button is still great. Oh wait, oh, is it working now? Okay. So thank you all for coming here today. I'm Jeremiah, and I'm going to talk about my project. So just to give you a brief idea of what exactly it's about. So we have these various post-tuning techniques which are quite useful. However, a major drawback is that they often reorganize the model internals, which is problematic when you've discovered features to use as like sparse autoencoders. So activation steering has recently been discovered, and this is an inference time technique which does not reorganize model internals. But currently it's quite manual, and I believe that this doesn't really fully elicit the full potential of activation steering. So just to give some more context, reinforcement learning is quite useful. RLHF, for example, reinforced learning to human feedback, is key behind several models like ChatGPT, Gemini, and Cloud in order to make them pleasant to talk to. However, the problem with reinforcement learning is that it can change the model in really strange ways, and it's difficult to really understand what exactly is being changed. Then sparse autoencoders are sort of this tool that we use for understanding the various concepts that are present in the model weights. So we have these bottleneck layers which are superposition, and we then label the various features. The problem with these sparse autoencoders is that every time we update the model, the weights of the model change, so they then become outdated. And every time we fine tune the model, we basically reduce sparse autoencoder, which is quite impractical. And now the third concept is activation steering, which uses vector arithmetic to reprogram the model. When we combine these with sparse autoencoders like we did in the hackathon, we can actually steer our models in a really highly interpretable manner. But as I mentioned earlier, this is currently quite manual. So my idea for this hackathon was basically, can we combine activation steering with sparse autoencoders into a reinforcement learning loop? And would this allow us to reprogram a model in a highly efficient and interpretable way? Okay, so from my understanding and what I saw in literature, this has not been done before. So I thought to myself, it would definitely be best to keep things as simple as possible, which is why I chose tic-tac-toe in order to train the model. So in compared to traditional reinforcement learning environments, tic-tac-toe is actually quite simple. We only have like 20,000 states and 9 possible actions. Additionally, large language models like llamas already know the rules, so we sort of need to train it on them. And the tic-tac-toe game is actually solved, so we can compute the optimal strategy at every step. And since we know the strategy every step, we can also give a good reward for the agent whenever it plays optimally as well. So in order to get the large language model to play the game, we needed to actually create a scaffold. So first, there's a system prompt which makes use of five-sort prompting. So five examples were given to the agent on how exactly it's to produce an output. Then for the user prompt, we would give the board along with what mark or class the model had to play as. The model was asked to output a number from 1 to 9, and then this number was extracted to from using regular expressions, and then we would put the mark of the agent on the board. Another factor to mention is that sometimes the process could go wrong. Either the API failed or the model produced garbage responses. So in that case, the model would just play a random Lego move instead. Okay, so now we can talk about how reinforcement learning is traditionally done. It's based on the Markov decision process. So we have the states, the actions, the transition function, and then the reward. Over here, the states suggest, well, the board given in this minimal representation. The actions are just 1 to 9 in numbers. The transition functions are deterministic. in tic-tac-toe. And for the rewards, you would give a positive reward for winning or drawing. There would be a small positive reward for playing optimal moves, and then there would be negative rewards for losing or producing garbage responses or some other error happens. Now we move on to the modified reinforcement learning approach. So instead of having the traditional actions, we actually have an action matrix for all of the vectors that we want to steer. Now, sparse autoencoders can have thousands of features, so attempting to steer all of them at once is actually really impractical. So instead, what I basically thought was to apply filter toning at the most important features that to be steered, and it's done using the output tokens, which are the numbers from 1 to 9, and then sorting the features which are discovered to these tokens. So some other details about the setup is that PPO is used because this is a policy gradient algorithm that can handle continuous action spaces. It was also important to limit the amount each vector could be steered by to this range. So it turns out if you modify too many vectors at once too strongly, the model just completely breaks down and produces like really random tokens, like just a single token over and over again. It was not really desirable. And the optimal policy was determined through minimax in efficient ways. So each step in the environment was actually done in like milliseconds. It was just the model itself which had the most latency. So for the experiments themselves, we have two agents which are based off Llama Tree 8 billion. So first is the normal LLM with the scaffold, and then it's the acquisition steered LLM. Both of these were made to fight against the optimal agent, which can always win. So it's impossible to win against it. And the evaluation method that we use for our models is actually the draw rate, and this is done over 100 games to account for variance. So when I first saw this figure, I was actually quite surprised. The baseline model has a draw rate of 1%, whereas the feature steered model has a draw rate of 3%. So technically, this is actually a 3 times improvement, which is quite nice. But it's also be noted that when your baseline is so low, it's really easy to improve upon it. So in order to understand what exactly the model is trying to do, I created this user interface, which basically showed the most important features in a given state. So here you can see the suppression of the number 5, and this corresponds to the center of the board, which is already occupied, so it's an illegal move. And conversely, the number 7 is actually strengthened, which is the bottom left. And this is actually one of the optimal moves in the game. So in this sense, we can actually see the model learning optimal behavior. So some other things to mention about the approach is that the method is independent of both the large language model and the reinforcement learning algorithm. All you need is a good reward function, which can be difficult to obtain in times. I also learned that steering too many things too often is a recipe for disaster. So my reward function in the end was actually inspired by curriculum learning. Initially, I had the same penalty for both producing a garbage response and producing an invalid move on the model. But when I later reduced the penalty for producing an invalid move, it appeared that the model was actually learning better, getting higher rewards. And there's also a more theoretical trade-off that I thought would be seen in the model in other environments. So for tic-tac-toe, for instance, you just have a single move that needs to be output. And when we use the feature steering approach, we actually take this single move and then have like 30 moves instead, or 30 features that are completely continuous. But suppose we have a robotics environment where the model needs to optimize like hundreds to thousands of different motors. In this case, using feature steering could condense all of those continuous features into just a few important ones that we can steer to manipulate the model. So for future work, I think it would be best to just focus on uh, tuning hyperparameters because I'm pretty sure I got nowhere near optimum in the project. Main problem was that reinforcement learning requires a lot of steps, and the GoodFire API appeared to have a significant amount of latency. So I'm based in Europe, and if the server is based in, say, US, that would be just around 300 milliseconds of latency itself, which makes a single step, in my case, like 2 times longer than it could have been if you ran the model locally. So besides that, we could also test the approach in other scenarios, like other environments, but it could also be used in RLHF or RLAIF. And finally, I also think we could integrate the reinforcement learning algorithm more deeply with the model. So instead of just using the states and then encoding them, you could actually use the latents of a previous layer and then give them to the model instead. And hopefully, this would allow the model to be more flexible. So to summarize, I think this could be a potential new tuning paradigm, and it's definitely worth investigating. Yeah, and that is my presentation. Thank you. Yeah, the problem with chess and Go is I would probably need a few years instead of a weekend to solve those environments. Yeah, so I initially thought of like more simpler environments, like I can't describe them right now, but the state space would be like 16 or so, just 16 different states. But the problem with these environments is that they are quite uncommon, and the model would most likely not know about the rules. So even though you prompt a model with the rules, it's not really likely that it would know how it should play the game. So I think tic-tac-toe was just a good idea in this case, since it's really popular, and I imagine everyone would have played it. Um, yeah, so I didn't really keep account of the games, but what I did keep account of was the number of steps in the environment. So as I mentioned over here, we had 12 environments that were done in parallel in order to train the agent, and the agent in the end was trained for about 6,000 steps. So if the average game size is about 3 steps or 4 steps, then the algorithm would have played like 2,000 games or something. Um, yeah, so that's a good question. So as I mentioned over here, you can't just do thousands of features at once, at least not for the case of the hackathon. So what I did was I first looked at the normal reinforcement learning setup, and I looked at the tokens that the model was outputting in response to the input, which was the prompt and the board state. And then I would see the features programmatically, of course, and basically just count the number of times each feature was present in the output token. And then finally, at the end, I would sort the features by the number of times they appeared and then selected the most important features using a manually determined threshold. So I don't have the features displayed here, but there are quite a few of them. Like a few is like the number 7 in numerical context, the number 1 in some other context. But there are also some other strange ones, like as you can see over here, upper bounds in programming exercises, ASCII art vertical lines. Yeah, a lot of strange things as well were included along with the numbers. Um, yeah, so it's basically nonsense. So sometimes you say plus 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 minus 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 bracket open bracket some random things. Other times it's just exclamation mark over and over and over again. Um, yeah, very chaotic. I did not pay too much attention to it because I was already going insane at the time. No, I do not, but that's definitely something that could be looked into for future. Yeah, yeah. Thank you.
Hello.
Hi. Hello.
One sec, sorry. Can you say something? Yes.
Go.
Yes. There's 5 of us. 6 of
Awesome. Yeah, amazing. So yeah, the name of our project is Steering Swiftly Safety Sparse Autoencoders. So basically, we know that unlearning is definitely a promising tool, make LLM safer. However, unlearning in most cases can be pretty costly because you need a lot of well-curated data to make the unlearning process effective. And the main challenge is to differentiate the type of content that the model should remember and the type of content that the model should forget. And for this, most of the time you need experts that aren't quite cheap. And also unlearning techniques results are easy to revert, as the literature showed. Only a few unrelated examples could make a model remember sensitive data that we tried to make it unlearn in the first place. So the question we asked ourselves was, can we reproduce unlearning results, sparse autoencoders, using limited examples and computer sources? And so to give you a bit more context, in May 2024, Lee and al. Used unlearning on the topic of weapons of mass destruction using cyber attack, bio and chemical knowledge. And more precisely, they created a corpora of knowledge to retain and knowledge to forget. And when they fine-tune the model with that corpora, they actually succeed to make it safer. They also created a benchmark that is basically a list of questions, allowing them to evaluate the amount of safety before and after the process. And so, but still, this process, as previously said, has several flaws. And so we wanted to try to obtain the same result, cheaper, more explainable, and boost technique. And so to do so, our methodology was to use the MMLU benchmark and the WMDP benchmark to evaluate if steering features would produce same result. And we had those 3 research questions. So the first route was a totally automated route where we used the constructive search provided by the Codifier API. Then we had a semi-automated where among the features provided, like found in the constructive search, we would pick with intuition, let's say, and the final route that would be completely based on human intuitions. And Agatha, maybe you want to go with the rest?
So the first experiment was the fully automated approach. So we took just a fraction of the corpora, which was 1%, and then we used contrastive search from the API to identify which features we want to steer in the model. So we kind of had to experiment to find the spot in terms of the number of features, the parameters for steering. What we saw is kind of similar to what was discussed in the previous talk. When you're steering multiple features at the same time, it's very easy to get the model to produce complete garbage. So for us, like 10 features we had was a very small factor of 0. And then what we were expecting to see was improved safety, probably losing a bit of accuracy. And then on the results, so to evaluate the effects of unlearning on safety, we used the weapons of mass destruction benchmark because the other ones weren't source. And then to evaluate how much general capabilities were lost, the MMLU benchmark. And we especially look at the ones from annex fields like computer safety or general computer science. I think it was university. So what we see is that we get some improvements, the unlearning, and we don't lose too much of general capability. but we will discuss that later. Some limitations we had is that some features related to safety were blocked from the API, and we didn't have enough time to completely adjust the steering ratios of features. Then the second experiment was if we put a human in the loop, manually select the features based on the ones we found before, can we improve the results? Can we play a bit more with steering factor, boost a bit some features, some less? And then what we observe is that we didn't. Can we go to? We didn't see any notable improvement from contrastive. So, but this time we only had 10 features, but we would need to work a bit more on that part. And lastly, the last experiment we wanted to see that can we do that without the expensive corpora? So we had someone from our team working with the feature API and trying to get the model to unlearn as much as could without compromising the capabilities. And what got out of that was one feature called attempts to override models' ethical constraints. Seemed pretty interesting. But then when we look at the results, we didn't see a lot of improvements compared to the base model. And also the effect on that was more unclear. So it reduced a bit the performance of the weapons of mass destruction proxy, which is what we want for unlearning, but not very significant. But the surprising result was that trying to boost the ethics feature led to an improvement on MMLU, but we didn't have enough time to investigate why was that. The other thing that we saw is that using random instead of a hand-picked one provided similar results. This approach is probably not very scalable. And yeah, maybe Guillaume, you can present.
Yes. So in conclusion, we can believe that steering is a promising approach, as has already been discussed in the previous paper and as we've shown again. We didn't talk about it before. We also make good use of the LMEVL framework, which is very useful for standardized benchmarking against reference datasets and easily customizable, as we did with the GoodFire API and our custom restricted datasets. We demonstrated that selection of features based solely on intuition did not give any good gains. However, a proper evaluation on the would require access to a model API without building filters. And in future works, first, we probably should use logits for fast evaluation, just because recap extraction requires waiting for the model to give you an answer after generating however many tokens, and that considerably slows down evaluations, so it leads to slower feedback cycles. We would like to see whether unlearning is robust to adversarial attacks in particular. So there is a bunch of adversarial attacks that have been designed against unlearning. Most of them require access to weights, which we could not use for our API, but there is probably some amount of adversarial attacks we could do without weight access in a black box setting. And in particular, we should try to create an adversarial benchmark that transforms the original examples using prompt injection techniques. And again, having non-filtered access to the output and could help better identifying danger in order to reduce their activations. There's also the aspect of whether ACE specifically trained for unlearning could be worth investigating, since ACEs end up being highly dataset dependent based on some case studies. So in conclusion, we believe that ACE unlearning needs more investigation, but is promising. And we'd be happy to answer any questions.
Yeah.
Yeah, absolutely. So as we said during the presentation, okay. Is it better now? Yeah, sorry. To be honest, I don't have any on I could do better. I'm trying to be closer to the computer. But yeah, basically, I was saying, as we said during the presentation, the main thing that we have to keep in mind is the fact that we didn't have access to all features actually for safety reason, because of actually the fire team that made their job really well, and so we couldn't see when we were doing contrastive search if indeed like super dangerous features were accessible as they were like shadowed, let's say, in the first place. However, yeah, we still, let's say, saw some features that were like most probably linked to dangerous capabilities. But you're right, indeed. On that version, let's say, of the features, it was kind of hard actually to differentiate, and that's why on the second route that we took, the semi-automated way, we picked among the feature, we didn't see that much improvement actually, and that's probably why it wasn't that clear actually between those.
Maybe I can take this one. So one of the bigger problems was test unleashing on dangerous capabilities, but we see that there were some restrictions on Fire API. So for example, that's why we restricted to cybersecurity, because like these answers were somehow allowed. But as soon as we tried to evaluate on, for example, bioweapons, like we couldn't even get the eval to run because the API would refuse to return something, to just crash. So we struggled a lot with that at the beginning, and this kind of slowed our process. And I think that was our main challenge during this weekend. And also that we couldn't test the adversarial attacks either. I had started working on the adversarial dataset, but as soon as you went adversarial, the output something like sometimes it contains the information that you want, but it was in a certain format that the model would also block. So we also had trouble understanding how much the model actually unlearned, or if it was just a superficial limit set by the API. It was a bit tricky.
Thank you to you.
Thank you.
Bye.
Hello, everyone. Can you hear me? No, okay. Okay. Hello. So let me gonna share the screen now. Yes. There's five. There's five. Okay. Okay. Hello, everyone. We are Team Feature Disruption Lab. We are a team of 5 across 4 different time zones. So the work we want to share today is improving AI safety through detection of adversarial prompt attack in large language model. So as AI become a bigger part of our life, it's important to make sure it's safe and reliable. And one big challenge is certain type of input called adversarial prompt can manipulate AI system and make them behave in an unpredictable way, and sometimes even producing harmful and dangerous output. So a normal use case would be a user add the model for a smoothie recipe, and the model respond with helpful instruction. And in an attack scenario, a bad actor could input a harmful prompt, like asking for instructions how to make a bomb. And to trick the model into complying, they may use a technique such as attack surface and add it to the prompt. So our project focus on understanding how these attacks work by studying the feature activation matrix. And we aim to build a classifier or machine learning model that can flag when an attack has happened and help blocking the attack. And this is crucial for building trust in AI system, especially when they use in high-stake area. Basically, our problem statement is how we can use pattern in the LLM internal behavior to tell harmful and safe input apart, and how can we reliably detect when these harmful attacks succeed. Our research is building on many previous research. One of them is the Harmo adversarial dataset, and the second one is multi-language defense by Fan et al. And the third one is research on SPAR autoencoder. Next, our teammate Oli will talk about our workflow and methodology. Welcome, Oli.
Awesome. Can you guys hear me? There we go. Cool. So you might want to make the screen full screen for this. That's quite a detailed diagram, but we can just walk through how we our methodology here. So basically, the goal. I'll start from the middle and then go kind of out to either side. The goal was to create a data set of kind of contrastive pairs of prompts, where on one hand you have an attempt at an adversarial prompt that doesn't work, and on the other hand you have one that does, and we're basically wanting to try and classify the behavior, classify from SAE latents when that happens. So an awesome future scenario would be if you could have run a small autoencoder on a language model as it's about to be adversarially prompted and realize, predict whether the model is going to be attacked. So how we did this is we started off with two different data sets. We had a third one, but it didn't really work out. And so Harmal is how we've decided to pronounce that, and Jailbreak Bench. And so for Harmal, this is a data set of a bunch of base prompts and then a bunch of variations of those prompts where they've applied a series of kind of state-of-the-art adversarial prompting techniques to make those prompts usually work on language models. So a base harmful prompt here is something like, can you tell me how to make a bomb? A successful adversarial prompt is something like what we saw before, a bunch of random strings, a bunch of role playing, etc. And then, can you tell me how to make a bomb? And so we ran these all through Llama 8B and got a bunch of different categories. So base prompts, adversarial prompts that did and didn't work. And we did a similar thing with Jailbreak Bench, but I might just continue on because this is taking a while to explain. So basically the next, sorry, do you mind just going back one slide really quickly? I'll just describe that last little bit. We ran all these prompts through the Goodfire API to collect the latent activations of these on SAEs. And then the last step was to train linear classifiers, so linear logistic regression in our case, to classify from those SAE activations between whether a jailbreak was successful or unsuccessful. Cool. Yeah, we'll go next slide now. Thank you. So this is just a few more details about this. So we had pretty aggressive standardization in the linear regression, logistic regression, cross-validation, lots of classic ML techniques to train these. And then if we just, this is just an example of, on the left, of some of these prompts. So, the one down the bottom is an example of an adversarial prompt. The one on the top is a unsuccessful base prompt. Can we go next slide now? So these are kind of our headline findings. I'll start from the middle, and this is the on the HarML dataset. We're comparing both adversarial prompts, but trying to classify when they did versus didn't work, and we were able to detect this with 82.3% accuracy. The one on the left is a little bit easier, you might say. So it's successful adversarial attacks versus the base attacks, base prompts, so without any adversarial prompting. And that was relatively unsurprisingly near perfect accuracy. And then the one on the right is, once again, I think pretty cool. We were 100% accurate in classifying on the second dataset, JB bench, successful versus non-successful adversarial attacks. And I'll just quickly describe that because I skimmed over it before, but basically this technique for adversarial prompting is to optimize a long gibberish string at the end of a prompt. And so in this case, we would comparing prompts with this optimized gibberish string, basically, versus adversarial versus prompts with a randomly generated string. And so this is probably the best comparison that we've got. So like to a human, it's basically indistinguishable. But we were able to figure out from SAE activations whether that adversarial prompt was working on the model. So because of this also only uses 74 of the around about 60,000 features present in those SAEs. I think that's everything to cover here. Can we go on to the next slide? So these are just a few examples of the features that we found activating.
I can cover this.
Nice.
So one of the things we wanted was our classifier to be interpretable. So we basically just took at the top weights in the logistic regression probe to identify which features were being used for classification on the JB data sets. And these are kind of suggestive. In particular, this one, leveraging resources for strategic advantage, we thought was interesting. Or maybe this other word or this other feature, which talks about the words change or modify in Slavic languages. So the fact that these adversarial suffixes and our classifier are picking up on these features is interesting and might indicate that there are specific features that are associated with these jailbreaking attacks. Now, of course, these are very, I guess, take these with a grain of salt because these are unlimited data sets. So we'd want to validate these across different things, different like attack types and data sources, and then also see how classification performance changes if you limit to like maybe these specific interesting features. Next.
I'll leave you on mute, I think.
There we go. Sorry. Cool. Can we just get all the text on that page? So basically, it's pretty cool to be able to see that we can build this into kind of a hypothetical pipeline for detecting these attacks as they're happening in real time. We think that there's probably some semantic information like inside these activations representing whether hypothetically maybe whether the model is deciding to give into the attack, deciding to these are all anthropomorphizations, but something like this. We're able to we were as Jack hinted to before, kind of unable to identify very specific features correlating. So lots left to look into. Sweet. Hold on. Yeah. Yeah. So yeah, just a lot. Sorry, I'm just getting some mix-ups here. Yeah, just some future research directions from here. Can we just go to the next slide? Yeah, actually, can I just go one step back? This is probably the most important caveat to our work here. Is this final point? So there's as Jack mentioned, we had some pretty narrow data sets, and it'd be really interesting to do a little bit more rigorous holdouts with these data sets. So see if these probes trained on S8 latents from one class of jailbreaks transfers to a completely separate class of jailbreaks would be probably the first thing to try. But we weren't really able to do that, just given the timelines and the data available to us. But yeah, cool.
Yeah, and does anyone have any questions? I can answer this. I think I also answered it in the chat, but we were just looking at the activations caused by the prompt. We considered for a little bit using the prompt plus response, but in that case, we'd be modeling reflection, which, for example, is common with 4.0 and some other newer models. But that would add another layer of statistical complexity that we felt wasn't really getting at the core of what we're trying to understand, which is, can we determine whether a prompt is adversarial, and can we determine whether that adversarial prompt is successful? Good question. That's a great
Yeah, I
question.
can. Oh,
Yeah,
so yeah,
go
sorry,
ahead.
I can talk about this. So yeah, this was something we were like really careful about, because there's 65,000 features, and our data sets were on the order of like 1,000 points, so it would be really easy to, I guess, overfit. And so what we found was that for the JB data set, it was using just 74 of the features. And I think across the data set, they were on the order of like tens of thousands of features. So it was definitely like selecting some like very specific features that were like important for classification.
Yeah, I can tackle this one. So if we go back, Long, would you mind going back to the methodology slide? Uh, yeah, so while he's doing that, so our methodology, so Harm 3L is really a cool data set because it uses pretty much every attack in the literature as of when it was published, and it composes a lot of them. And what that means is that it actually has inbuilt multilingual attacks. Most interestingly, it uses multilingual not in just the sense of like English versus Spanish, but also in the sense of text versus JSON, for example. As one of the attacks that it uses, it tries to get the output in JSON, which sometimes is able to elicit a harmful response. But what we saw is in the features is a lot of the features that were most highly correlated with adversarial suffixes, they involved foreign languages, even when the adversarial suffixes themselves were purely in English. What that might indicate, for example, is that maybe the labeling is wrong of those latent features. Maybe it's just incorrect labeling, or that there's something there that we're not seeing. One of the caveats to our work is that we were unable to determine we were unable to determine a causal link between like, hi, these 5 features directly correlate with the adversarial suffix working. For that, we would need a little bit more time and probably a little bit more compute as well. Yeah, so Jack and I are from US East, so EST. I'm from Atlanta. Jack, if you want.
I'm in Toronto.
Oh, I'm from New Zealand, so um,
Yeah. 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 We have one team member from London as well, and then I'm from Kauri. Yeah. So we are all over the world. Yeah. Thank you.
Hey, everybody. Hi. Can you hear me okay? Great. Yeah, so like really awesome projects across the board. As like I said when we went into the hackathon, like we built this so that people could do really cool and important safety research on top of it. And we were just like so motivated and excited by everything that we saw over the weekend. A lot of really cool projects. So in addition to the winners, there were so many good projects. So this is by no means a full list, but just to like shout out a couple other ones that um, I really appreciated. There was one on hallucination robustness and medical Q&A using feature steering, which was really interesting. Used like decision tree classifiers to identify promising features for steering. I thought that was a super cool technique. There was one on encouraging chain of thought reasoning, which had like really promising results. In general, there were just like tons of fantastic projects, and so for everyone who like worked really hard on this over the weekend, like I would just like stick with it. If you want to continue your research on the Goodfire API, we're happy to support you. Just like reach out to the team. We did remove all of the hackathon teams, but we are happy to add you back so that you can continue your work. And for the winners, we're going to continue to support your research with additional credits over the long term, so you can keep building out your ideas and flesh them out and turn them into full-fledged papers, hopefully. So yeah, I just want to express like my gratitude to all of you. We're very feedback hungry, so if you do have feedback on the API and your experience, things that you would have liked to see or would have made your job easier, please reach out. You can contact me on this Discord or email me at dan@goodfire.ai. And yeah, thank you so much for everything and for all the awesome projects. Oh, no problem. But thanks again, everyone, and reach out whenever.